Okay, so we're going to leave the financial model type questions, and then we're going to look more at a science standpoint. So this is we'll start with exponential growth and decay. And the only so you recognize the PERT formula again. Let me real quick clarify this here. This symbol, which is called a P naught, N-A-U-G-H-T, that's a science term. It refers back to what's called an initial condition or starting off condition. Kind of like in a bank account, it's a starting off amount, but you'll see this P naught notation typically in physics or science courses just to indicate what, before anything happened, this is what the initial thing started off to be. And just a completely silly note, and maybe this will help make the formula stand out in your head. But when I was in high school and I first learned about this formula, the PERT formula, PERT shampoo was a brand new product out there. And so you might have heard of PERT, P-E-R-T. And back when I was in high school, what made it so cool is it was the first time where I had shampoo plus conditioner. And I just thought to myself, wow, you only had to apply stuff to your hair once instead of twice. So like I said, very silly, but for me it's the shampoo formula. Okay. All right. So in the problem we're given, we're told we've got a colony of bacteria that grows according to the law of uninhibited growth. The function that describes its behavior is given, so they give us the equation. Now they're just going to ask us some questions. So given that formula, this 90e to the 0.05t, according to the formula, what would the initial amount be? And that's that 90, and we're measuring this in terms of grams. What number would represent the growth rate? So what would R be? And that's R is 0.05. So our population is growing by 5% each day. So we're measuring T in terms of days. And then we'll keep going. What is the population after 5 days? Okay. So in this case, they're asking when T equals 5, how many grams are there? So in that case, I just want N of 5, which is 90 e to the 0.05 times 5. And that'll tell me exactly how many grams are there. So let me go here, clear that out. All right, so 90, and then our e to the x 0.05 times 5. And so after 5 days, we have 115.56 grams. Okay, question, how long will it take to reach 140 cells? So if you think back to our formula, let me kind of write the formula down here, which is N sub T 90e to the 0.05 T. So we only have two variables that we could ever introduce in the equation. That's either T or the amount, so the N, and that 140 actually represents the N piece. And that means we're going to need to solve for T. Well, now this looks like one of our types of equations that we had to solve for. And in this case, the variable is buried up in the exponent. And so we're going to have to use the ln to bring the exponent out front. So that's my first task, is to isolate out the base with the variable. So I'm going to divide both sides by 90. And I can see that I can divide, let's see, I'm not really dividing zeros out. I'm dividing both numbers by 10. I end up with 14 over 9 equals e to the 0.05 t. And then I want to take the ln of both sides. And so on the left, I still have the ln of 14 over 9. But the ln of e to the 0.05 t, that's one of our properties. So when you think for a second what property that would be, and that simplifies down to 0.05 t. And so now I just need to solve for t. So I'm going to divide both sides by 0.05. And so I get the ln of 14 over 9 divided by 0.05. And so that's what I want to type in my calculator. So come over here. ln 14 divided by 9 divided by 0.05. All right, so I get that t is 8.8384. 8.84 days. Okay, and just be careful with directions. You know, be accurate as the computer wants you to be. Next question, how long will it take to double? So going back to our formula, you know, we've got that 90 there, so if it doubles, what number would it be? It'd be 180. So 180 equals 90 e to the 0.05 t. And then we just do the same thing we did a second ago, where I want to isolate out the exponent first. So I'm going to get e by itself. Now in this case I get 180 over 90, which is 2 e to the 0.05 t. Now that 2 should make sense because we're talking about how long it would it take to double. Then I want to take the ln of both sides. And so I have ln of 2 equals 0.05 t. And then divide both sides by 0.05. And so I get t is equal to the ln of 2 divided by 0.05. And then this is where I'd go to my calculator. And so ln of 2 divided by 0.05, and I get 13.86. So about 13.86 days would it take to double. Okay. Okay, so I'm going to do a little, I want to say not necessarily an experiment, but rather than just give you the formula for half-life and double life, I want to take just a brief moment and show you where we get these formulas from. That it's just not some magic witchcraft thing, that there actually are, that someone is following rules, and they're just manipulating just a general formula. And I don't expect you, as I'm doing this isn't something I'd expect you to do on a test, not as a specific skill, but as I'm doing the steps, you know, if there's a part where you're a little unsure about, well, why did he do that? I might write that down, and that would be something I'd ask in class or something I would email me, just to make sure that, you know, you should be able to understand the steps, is what I'm trying to say. Okay. Now, what I'm going to do is I'm going to start, because I want to do this in a very generic, general way, which is going to be very frustrating because I'm going to take numbers out and I'm going to try to put it in terms of just some very specific variables. And so what I want to start with is I want to say that in doing half-life or double life, you know, if it equals, if P over P naught, so if P naught, if the original amount is twice as much as the current amount, you know, that means I'm looking at 1/2, or if it's the other way around, you know, it's 2 over 1. Okay, and that means that we're dealing with half-life in the first case or double life in the second case. But either way, it's a number, and I would just want to call it the number A. So I'm just going to call this generic amount A, but it's going to be at a certain time. So at t equals, and I'm just going to, right now I'm going to call it B, okay? But going back here, if it's half-life, then B would represent sort of this half-time idea, the amount of time that it took half the material to disappear. And if it's double life, then it would represent the amount of time that it took something to double. Okay, So I've now got this A and this B that I'm about to bring up into the formula, so just bear with. Okay, so we're going to do our PERT formula. And again, I'm going to divide by P naught. And when I divide, I'm going to replace this thing with A. And at the same time, I'm going to replace T with B. Because remember, B is a specific time when that either half-life or double life occurs. Okay. Now, what is this going to allow me to do? Well, the only thing that's actually still a variable, I know it's there's a lot of letters floating around here, but A is actually a constant. It's at a specific time. B is related to A, so that's a constant. There's only one variable in that entire equation right now, and that's R. So I'm going to solve for R. And now, how do I get access to that? Remember, that's where I have to take the ln's. Okay. And so I have ln of A equals, and that ln of e to the rb just leaves us with rb. So if I want to solve for r, I'm going to divide by b. So I get that ln of a over b is equal to r. Okay, so that's half the, we're not done yet, but that's half the story that we have to understand, that what I now have is this rate is dependent upon whether I'm talking about half-life or double life. But it's going to allow me to rewrite a general formula in terms of A and B, and thus I can give a general equation. So now what I'm going to do is I'm going to go back in to the original equation, and I'm going to say, let's do P equals P naught, E, okay, instead of R, I'm going to replace it with this ln of A over B times T. Now, let me kind of point out a goal here, so you don't think I'm completely crazy for doing it this way. But if I can get it to say E of U, if I can get it to say E of the ln of something, that's just going to simplify down to the something. Whatever that U is, it'll reduce down to that. But notice the E and the ln are gone. That's what I want. I want to get the E and the ln gone. But I can't do that until I have the E and the ln essentially touching like they are in the formula. Okay, so let's look at the problem. Right now, it's the ln of A divided by B times T. Okay, so I'm dividing by B and timesing T. There's sort of the concern there. Is there another way I could write that, though? You know, right now the way I see it, it says I'm dividing by B first, and then I'm going to take that answer and then multiply it by T. But you know, honestly, if you're going to multiply and divide, do you have to divide first? Is it okay to switch the order around? And the answer is yes. We have one of our mathematical properties called the commutative property of multiplication allows us to rearrange a series of multiplications into the whatever convenient order we want. And so I'm going to rewrite this formula, P equals P naught E, and I'm going to pull the T and B out front of the ln of A. And again, let's kind of think about what that says. That says take T and divide it by B, and then multiply that by the ln of A. Isn't that the exact same thing I said before? Start off with the ln of A divided by B, and then multiplied by T. So I just kind of switched T in the ln of A's position. But now I can do that property where I can bring it up as an exponent. Okay? And so for a very, very brief second, we're going to have a very scary looking exponent. Okay, you ready for this? So E has an exponent of ln of A, and the ln of A has an exponent of T over B. So our exponent has an exponent. Very scary, right? But notice we now have E and ln touching right here. They're now next to each other just like they were up in that formula. And so now I can simplify it down to that. And so I get P equals P naught times A to the T over B power. Okay, now that's my goal. That's what I wanted to show. Because now I want to show you the two formulas that we have and what that sort of means. We have a half-life formula. Okay, and the half-life formula is P equals P naught, and remember half-life, our A would be 1/2, and it'd be T divided by half time. And then the double life formula would be P equals P naught, and this time instead of being 1/2, it's now 2 because it's the amount of time it took to double. That would be T divided by double time. Okay. So I could have just given you those two formulas. I could have just said, hey, here are two formulas that we're going to use. But instead, I wanted to take a brief second and show you that they're actually the same formula, and they're all derived using the exact same pattern that I just walked you through. Okay. So in this question, I want you to take a second and I want you to read it. And when you're reading it, go ahead and pause the video, read the question, and all I want you to do for right now is figure out if it's half-life or double life and why. Okay. All right. So hopefully you noticed that it's half-life, and the reason being, right there, that phrase, if the half-life of carbon-14 is 5,600 years. Okay. And now, if it's not asking if it is, it's more telling us that that's what the half-life is. So let me initially set up our formula. P equals P naught 1/2 T divided by, and now we need a time associated with the amount of time it takes for half of the material to disappear, and that's where the 5,600 comes in. Okay, so that's what our formula looks like at this particular moment. Okay, so the next thing is I need to figure out what am I solving for? What variable do they want me to find? So if you haven't had a chance to figure that out, go ahead and pause the video and look at the question, or try to figure out what question are you actually answering. Okay, and hopefully you got that we are actually trying to find T. So we want to know T is when. Okay, and then we got to look at what else we're told. Now we're given this really strange piece of information, this 1.67%. So what's going on here is they found somewhere on the ground, somewhere in the earth, and they happen to know that there's only 1.67% of the original carbon-14 still remaining in the material. Well, that's not really a starting off amount. That's not really an ending amount. It's sort of a ratio between those two. So if you think about P over P naught, okay, if we're talking that there's more material at the beginning and less material at the end, well, that's going to create some sort of fraction or some sort of decimal. Well, that's actually what that 1.67% is. So they're telling us that P over P naught is 0.0167. Okay, so our job is when P over P naught is 0.0167, what's T? How long ago did this event actually occur? So our formula, once we plug in our numbers, looks like this. We've divided by P naught, so that's why it's gone, and we're left with 1/2 T over 5,600. Okay, and so now we get to solve our problem. Okay, so in solving our problem, what do? Well, my variable is buried inside the exponent, so I need to take advantage of our log rules. So I'm going to take the ln of both sides. Okay, so on the left I have ln of 0.0167. Now on the right, we don't really have a way for the ln of the 1/2 to disappear. It's still going to be there, but we can apply that property that says the ln of A to the B comes out front, right? So we can apply that rule, so I can bring this T over 5,600 ln of 1/2 out front. Okay, so now what? Well, I'm trying to solve for T, right? Well, if I'm trying to solve for T, I'm dividing by 5,600. I'm going to multiply by 5,600 on both sides. Okay, And if I am multiplying by the ln of 1/2, then I want to divide by the ln of 1/2. Okay, so what does that look like then? That means in our calculator in a second, we're going to have to type in 5600 times the ln of 0.0167 divided by the ln of 1/2. And that's exactly what t means. Okay, so let me go to the calculator. And let me clear out my other stuff. All right, oops. Clear out everything. Okay, so 5600 times the ln of 0.0167. And I want to divide that by the ln of 1/2. Okay, and that gives us approximately 33,062. Okay, years ago. So in other words, this event, whenever the tree was burned down or cut down, happened about 33,000 years ago, and that's called carbon dating. But that's an actual job that someone has to make those measurements and figure those things out.